So we're now going to consider the way a radio wave interacts with a dielectric material, which is the opposite of the conducting material that we considered in the last lecture. Let's just start by writing down the geometry of the problem. So we're going to start out with a boundary. On one side of the boundary, we're going to have material. We're going to call it material 2. We're going to say it has a permittivity epsilon 2, a permeability mu 2, and therefore it has an impedance eta 2, which is simply the square root of mu 2 over epsilon 2. On the other side, we have material 1, which has the exact opposite. It's got an epsilon 1, it's got a mu 1, and it's got an eta 1. Right, this can be air and concrete. It can be foam and wood. It can be any two materials. What you are going to consider that both materials have no conductivity. Right, so these are just dielectrics. They are not conductors. Right. The problem of a dielectric and conductor can be solved mathematically, but we're not going to cover it here. All right, so these are both dielectrics. Now we have to consider 3 different waves. We're going to start out with an incident wave here. And I'm going to draw this with a k sub I. Again, k is the direction of propagation, and the I refers to incident. And as before, we're going to assume that this wave is coming in at a normal angle or 90-degree angle with respect to the boundary. We also are going to have a reflected wave, and it stands to reason, we'll prove this later, but it stands to reason that the reflected wave will be also coming out at a 90-degree angle from the surface, just like the incident wave was, just counter parallel to the incident. The difference is that in this case, we have to keep track of a third potential wave that's moving into the material, right? In the perfect conductor, we knew that there could not be a wave that goes into the metal. We can no longer assume that. So we're going to call this wave here k hat with a t for transmitted. Whereas r was reflected, and the I was incident. Okay. Now let's just write down the generic form of what the electric fields and magnetic fields would be for all of these waves. And let's do that off to the side. Oops. All right. So for the incident wave, we're going to have that the electric field of the incident wave, and let's just start off by assuming that there is a constant electric field that describes this incident wave, and that's a phasor. So E0I times e to the minus j, and there's going to be a beta 1 to it times z. And let's just assume it's oriented in the x direction. Let's just take that as a starting assumption. Remember, beta 1 is going to be 2 pi over the wavelength in material 1, or it's omega, the 2 pi times the frequency divided by the propagation velocity in material 1. Remember, the beta is going to be different on the other side, but let's just start out with this. Now, the magnetic field is always really simple. It's always just the electric field divided by eta. So I'm going to just put down an E0I here and just divide it by an eta 1. And we're going to keep the same e to the minus j beta 1z, and it's going to be pointed in the positive y direction, because we know that E cross H has to equal the direction of propagation, right? E cross H is in the k hat direction. Another way to write this a little more exactly is E hat cross H hat equals k hat, right? A unit vector in the electric field direction cross with a unit vector in the H direction in the magnetic field direction equals the vector in the direction of propagation, right? So that is the incident wave. All right, now we can write down the same thing for the reflected wave and for the transmitted wave. And I'm going to do that real quickly so we don't spend 5 minutes doing this. This will be ER, that's a phasor right there, equals E0R. We don't yet know what E0R is. It's just a generic placeholder for what that electric field is going to be, divided by 801. This is still propagating now in the positive direction, but it still has a wave number of beta 1 because it's propagating in material 1. And this will be in the x direction. And then there is the magnetic field reflected equals E0R divided by 801 times e to the positive j beta 1 times z, again in the y direction. Remember the placeholder here. Let's just consider directions for a second, because we know that electric field cross magnetic field has to equal the direction of propagation. So we got to add one more thing. We're going to have to put a negative sign right here on this y direction, so that x hat cross negative y equals negative z, since this is propagating in the negative z. So I'm just going to take that negative sign. I'm going to put it out here, and I'm going to get rid of it from here. All right, so that represents the, let me just keep it blue here. This is the reflected wave. Right now we got one more wave, which is the transmitted wave. And so that's going to be ET will equal to just a generic placeholder, an unknown constant, E0t as a phasor, times e to the negative j beta 2z. There's a negative j because it's still propagating in the positive z direction, but I'm going to make it a beta 2 because now we're in material 2. The transmitted wave is in material 2. So this is in the x direction. And finally, the transmitted magnetic field, I'm just going to take that placeholder, E0t, and I'm going to divide it by a to 2, and I'm going to keep the same complex exponential, e to the minus j beta 2z, and that'll be pointed in the y direction. And this is our transmitted wave. All right, so that just describes these three waves, Ki, Kr, and Kt, and the electric field and magnetic field associated with them. All we've done is we've maintained the relationship that the electric field divided by the magnetic field has to equal the impedance. We've maintained the relationship that E cross H is in the direction of propagation. And other than that, we just have these placeholder variables for the electric field of the incident, reflected, and transmitted wave that we don't know, but we're going to come up with ways in which they relate to each other using boundary conditions, right? So those are unknowns. But let's also write down our boundary conditions just so we can have access to everything. And we'll identify which ones we actually want to use in a second. But let's write down our boundary conditions, which is that n hat dotted with d1 minus d2 equals surface charge. There's n hat dotted with b1 minus b2 equals 0, right? Remember, n hat is the vector that points into material 1 that has length 1. N hat cross with E1 minus E2 equals 0. And finally, n hat cross H1 minus H2 equals JS. All right. Now let's make a couple of assumptions here. All right. Remember, these are boundary conditions. And so they only apply on the boundary. They only apply at z equals 0. They don't necessarily apply anywhere else, but we can assume that they are true at the boundary at z equals 0. Now, we did assume before that we have no conductivity. These are pure dielectrics. And so for that, we can make a couple of simplifications. This rho s has to be 0. In order for there to be charge, you have to have current that flows and builds up that charge. And since there's no conductivity, there can't be any current, which also means that this Js has to equal to 0 because we're assuming a perfect dielectric and something with no conductivity. All right. So let's take a look at this. And the main boundary condition that's going to be useful for us is this one, this n hat cross E1 minus E2 equals 0. So let's apply this directly and see where it leads us. All right. And remember, E1 and E2 are the electric fields at the boundary. So let's figure out what E1 and E2 are. By going back to our definition of what the incident, reflected, and transmitted electric fields are. So if we set z equal to 0, all the complex exponentials fade away, in which case E1 evaluated at z equals 0 is going to be the sum of the incident with the reflected wave. All right, so it's going to be E0I plus E0R as a phasor, right? Again, take this electric field, set z equal to 0, so its complex exponential disappears. And this is oriented in the x direction. All right, so that's what E1 is. E2 can also be figured out. That's the electric field on the number 2 side of the boundary. And that's simply going to be equal to just the transmitted wave, which equals E0t pointed in the x direction. So we're going to take this right here and we're going to apply it to our definition of this boundary condition right here. Right. So the way we set up this boundary condition is we're going to have a 3x3 determinant. The first row of that is going to be x hat, y hat, and z hat. In the second row, we're going to write out the 3 components of n. And remember, going back to this initial picture, n by definition points into material 1, meaning this right here is n hat. So n hat is basically negative z direction. It's negative z hat. So the way we're going to represent that is with this right here, is with a 0, 0, and a negative 1, right? Because n hat is oriented in the negative z direction. All right, so this second row is basically the n hat portion of this. Now in this third row, we want to put out h1 minus h2. And since h1 and h2 both have only a couple components, we're gonna simplify this. But first, let's figure out what h1 and h2 is, since we only wrote down the electric field. All right. All right. You know what? I made a little mistake here, which is I actually want to use this boundary condition here. So let me just erase this. I want to use the 4th boundary condition, not the 3rd one. Right? No, sorry. Got that correct. All right, so let's now write down E1 minus E2. In the y component and z component, both E1 and E2 are 0. So that's pretty simple. This will be 0, and this will be 0. And now we're going to take E1, the x component, which is E0I plus E0R. I'm going to indicate that those are vectors. And we're going to subtract E2, right? Which means E2 is going to be E0t. So there's going to be a minus E0t for transmitted right here, right? And we're going to set this whole thing equal to 0 this is simply plugging into this boundary condition. Now let's work this all out. And if you expand this, you're going to end up with the following. You're going to get that E0I plus E0R minus E0T equals 0. Right? If you expand this out, you're going to get this condition. Right? Now, that's not enough information to solve everything, but it's a piece of the puzzle. So let's leave it right there. Now, the next thing we're going to do is we're going to apply this boundary condition, n hat cross h1 minus h2 equals 0. And I'm going to set that up down here. This will be x hat, y hat, z hat. And again, we'll have 0, 0, minus 1. And this will be E0I as a phasor divided by eta 1 plus E0R divided by eta 1 minus E0T as a phasor divided by eta 2. And then a 0 and a 0. And again, that equals to 0. If you expand this out, expand this determinant, then the equation that you'll get is E0I divided by eta 1 plus E0I divided by eta 1. Sorry, that's an R right there. Minus E0T divided by eta 2 also equals 0. And these are all phasors, by the way. Now we've got 3 unknowns and we've got 2 equations. What that means is that if I can specify one of these 3, I can get the other 2. I've got enough information to do that with this system of equations. These 2 equations are independent because eta 1 and eta 2 are different, right? So this is 2 different bits of information. And so you can put this together, and let's say we know what the incident electric field is. From that, we can figure out what the reflected and transmitted wave is. And we're going to first define the reflection coefficient gamma as being the ratio of E0R divided by E0I. It's the ratio of what's reflected to what's coming in. That's the reflection coefficient. If you solve these 2 equations, you can rearrange them to figure out what E0R divided by E0I is, and it works out to be the following, and this should look familiar. It's going to be eta 2 minus eta 1 divided by eta 2 plus eta 1. That should look very familiar because back in the transmission line days, we calculated that the reflection coefficient was the load minus the line divided by the load plus the line. It's the same equation. In this case, the load is the intrinsic impedance of the second material, the one that's on the other side of the boundary. And eta 1 is the material that comes up to that boundary, where the wave is incident up until that point. Right, so this is what we might call the reflection coefficient, and it has the exact same form as our transmission line days. We can also define a transmission coefficient. We'll call that tau. And that will work out to be one plus gamma. It's going to work out to be, if you plug this in precisely, it's 2 times eta 2 divided by eta 2 plus eta 1. Again, you can solve these equations. This equals the transmitted electric field divided by the incident electric field. And if you solve this equation to give you this ratio, this is what you're going to get for the transmission coefficient. Again, same exact formula as the transmission lines. All we're doing is replacing voltage with electric field and replacing currents with magnetic field. And all we had to do to come up with this was apply these boundary conditions directly, and we had a system of equations, 2 equations, 3 unknowns, and from that, we know that if we specify one of the 3, we can get the other 2 via these relationships here. All right, so that basically reminds us that a wave reflecting off of a dielectric is going to work exactly the same as how a transmission line wave reflects when we have Z0 and it reflects at a boundary with another transmission line. Let me just be consistent. I'll call this Z1. Sorry, prove that. Z1 and Z2. The reflection coefficient right here was Z2 minus Z1 over the sum. And that's exactly the same definition that we have with complex impedance. We also have the transmission coefficient tau, which equals 1 plus gamma. And that, again, is exactly the same. So the radial wave reflecting off the dielectric boundary is exactly the same as the voltage wave reflecting at a boundary between 2 different transmission lines with 2 different intrinsic impedances. Now, things will change, and I won't get into the details here. Things will change if we have oblique incidence, meaning a case where we have a wave coming in at an angle. We are going to have a reflected wave that comes over here. So this is incidence. This will be reflected. And this angle theta right here will be the same as this angle. These 2 angles are equal. In addition, we're going to have something called a refracted wave, which will transmit into the material. That angle theta 2 will be different, right? So this is theta 1. And these 2 angles are the same, but this angle theta 2 is not necessarily the same as theta 1. And that's called the refracted wave. The way you determine this relationship between theta 2 and theta 1 is with something called Snell's law, which we won't cover here. But this scenario, this more complicated scenario of oblique incidence, as it's called, can also be solved simply by applying those boundary conditions, and you get a system of equations, and you can solve everything together. There's just a couple more terms to it, but it's still the same exact process. But that is beyond the scope of what we're going to consider here. But just wanted to give you a flavor of what would be next. All right. So that concludes this portion where we're now talking about how radio waves reflect off of objects that are dielectrics. This is very useful, for example, if you have a radar reflecting off of rubber or off of something that's not a good conductor, then this will basically describe how that process is happening. Now, this assumes we have a nice flat surface, a nice perfect conductor, and you've got a radio wave that's reflecting off of it. If your conductor is, if it's curved or if it's got jagged edges, then that process is a little more complicated. That is well beyond the scope of this course, but it's all solvable with the exact same principles of what you're seeing here, applying boundary conditions and arriving at a system of equation that you can solve. That's where we'll leave it, with an eye toward much more complicated applications, but this is basically the underlying principles by which radio wave reflects with any object or any material.